Okay, so you want to know just how off your time could be based off of the uncertainty that you had in your distance and your velocity. So time is going to be your dependent variable. It depends on both the distance and the velocity. In this case, our units is hours. This distance and this velocity are your independent variables. They're the things that you measured independently. So we have distance, and we saw on the sign that was 57 miles. And we found out there was an uncertainty of about plus or minus 1 mile, and we don't have any sort of confidence interval on that. The source of that uncertainty was in effect instrumental. We used the sign as an instrument to find that. Our next independent variable is the velocity, so we write that in there, and our average velocity was 70 miles per hour, and we know, or we found, that that had a uncertainty of 3.64 at 95% confidence. And the source of that uncertainty came from both the instrumental uncertainty and our statistical uncertainty. Now we only have two independent variables, so we don't need to use these things. They can just be erased. So now you know what the distance is, you know what the velocity is, you have the uncertainty on each. The question is, what is the uncertainty on the time? How much can your time vary based off of the variation that you see in your distance and your velocity? In order to calculate that, you're actually going to have to find the partial derivative of your dependent variable with respect to each of your independent variables. What that means for you for this problem right here is that for each of these independent variables, distance and velocity, you're going to have to find the partial of time with respect to distance and velocity. So this equation here, the first one that we're going to do is we're going to find the partial with respect to the distance. And the partial derivative is actually easier. It's actually easier in a lot of ways than one might expect, because we can, when we're trying to find the partial derivative of, say, this distance with, or sorry, this time with respect to this distance, any other term that you see in there then acts like a constant. So in this case, we could just imagine that this equation was time equals distance over 2. Now the velocity is obviously not 2, but for taking the partial derivative purpose, that velocity is like 2. It's like a constant. It won't be 2, but it doesn't really affect us as we're trying to take the partial derivative. The derivative of time with respect to distance for this equation is fairly trivial. It just turns into 1 over that constant. The same thing's going to happen when we take the partial of time with respect to distance. This velocity that we see here is just a constant. So when we take the partial derivative of time with respect to distance, we just end up with 1 over the velocity. Now when we're going to do the partial of time with respect to velocity, we can once again imagine our simpler equation. So time now in this case is going to be equal to, I'm just going to use the same constant, 2 over v. Notice here the velocity was the constant. I just picked 2. You could pick pi if you wanted to, just some random constant. But for now, for this case, velocity is the thing we're interested in, and so we make the other thing a constant. And if we had a bunch of other variables in there, so we had 3 independent variables, the variables that we're not interested in would all just become constants. So then this equation here, finding the derivative of it, is a little easier. A little harder than the last one, but it's still not, oops, forgot my constant. It's still not as complex as it might have seemed when we first talked about taking a partial derivative. So I'm going to do that now for this part down here. If I take dt dv, we're going to end up with negative d over v squared. This part here is not very useful to us because if you just look at these two things, obviously they're going to have different units. So we don't need to worry about that, and the same will be true over here. And this space here is just for you to fill in your variables. So 1 over v is going to be 1 over 70 miles per hour, which is going to give us 0.014285 hours per mile. down here, negative d over v squared is going to be equal to negative 57 miles over 70 miles per hour squared, and that is going to become negative 0.011632. And now we've got just about all the pieces that we need to actually figure out what the total uncertainty on our time is. So if we scroll down, and we don't need these blocks, we only had two independent variables, so that goes away. So our uncertainty on our time is going to be the partial of time with respect to distance multiplied by the distance, the uncertainty on the distance, and we'll square each of those terms, and then we'll add to it the uncertainty on our time, and we'll add to it the partial of time with respect to velocity, square that, and multiply that by our uncertainty on our velocity and square that. We don't need these terms because we only had two independent variables. So, all right, so we can write this out as one big giant square root. And it's sort of up to you. Some people like to take these values and then just plug them right into this and just square this term. So this term here would just be squared, as you see here, and then multiplied by the uncertainty squared. Some people like to write out all of this because sometimes you may find that then pieces cancel and it makes your life easier. Whatever you're most comfortable with. For completeness sake, I'm just going to write out each of these terms and then write down the results that I get from multiplying things. So I'll have 1 over 70 miles per hour squared. That is this term here. That's the partial of my time with respect to my distance. I'm going to multiply that partial derivative by the uncertainty in my distance, which was 1 mile. That gets squared as well, and the square root just keeps going on. I'm also then going to add to it the uncertainty that I would expect to see in my time because of uncertainty in my velocity. So that's where I'm going to take this term here, which is this partial, and that's going to be negative 57 over 70 miles per hour. The 70 miles per hour is squared, and the negative 57 over the 70 miles per hour squared is also squared. So you notice I have two squares in there. Please be careful with the squares if you end up with more than one. That then gets multiplied by my uncertainty in my velocity, which was 3.64 miles per hour, which is also itself squared. If you aren't sick of the squares and square roots yet, then you're doing something wrong. So then I can write all this out after plugging stuff into my calculator as 0.01428 plus 0 squared plus 0.04234 squared. Do the math on that, and the total uncertainty in my time comes out to be 0.04468 at 95% confidence hours. Since no one really thinks in terms of fractions of hours all that often, we can go ahead and convert this uncertainty into minutes, and I'm just going to go ahead and pull in my time was 48.85 minutes, and this uncertainty in terms of minutes is going to be plus or minus 2.68 minutes. So this means that we actually have a range of times that are allowable. In fact, the range is going to be 46.18 through 51.54 minutes. Notice that 51.54 encapsulates the 51 minutes that we saw from our trip. So we actually did a pretty decent job in predicting. Even though we didn't get it exactly at 48.85, we're still within the range that we would expect for the uncertainty in the data that we collected. Now, when we are thinking about what causes this range, what causes this uncertainty, we can go back and look at our two independent variables and the uncertainties they produced, compare those, and actually figure out what is causing the uncertainty. What is our largest source of uncertainty for our dependent variable for the time? In order to do that, what we can compare is this term with this term. Notice we don't want to just compare these two, because these are just the partials, and we don't want to compare just the uncertainties on the measurements. Neither one of those pieces is complete. We need both the partial and the partial of the dependent variable with respect to the independent variable and the uncertainty on that independent variable. Those two terms together will create the total uncertainty that we expect in our dependent variable from our measurement of the independent variable. So when we can compare these two, and this 0.014 came from our distance and this 0.04 came from our velocity. So this one, the uncertainty on the velocity, is larger, almost 4 times larger than the uncertainty on our distance. So if you're looking for someone to blame, you need to blame your friend. Your friend actually has a large enough variation in their velocity that you get this sort of range in times that you would expect. So if you wanted to do a better job with your prediction, your friend should probably use cruise control. Okay, so the next question is, how does the uncertainty that the distance and the velocity have actually affect our uncertainty on the time? In order to find that, we're going to have to find the partial derivative of our equation for time with respect to both the distance and velocity. So if we scroll up just a bit, we see that our so we want to know, crackerjack. So just knowing the uncertainty on the distance and the velocity is not enough for us to be able to just directly calculate the uncertainty on the time, because time isn't just dependent on just distance linearly and velocity linearly. There's a equation. Fucking A, man. So in order to find out how this uncertainty on our distance and this uncertainty on our velocity affect our uncertainty on the time, or go into creating the uncertainty on our time, we'll need to take this equation here for our time, and we're going to actually, for each of the dependent variables, calculate what the partial derivative of time is with respect to that independent depend we're going to find what the partial derivative of time is with respect to each of those independent variables. So here we have dt, dd, and down here we'll have dv, or oh man. And down here we'll have dt, dv. So if we look at this equation, I'm going to write it over here.